let's take a look at functions. Now, a function, mathematically speaking, is a relation between two different values or two different variables, and it's kind of a specific relation such that any input that you put into this equation or function will result in exactly one output. So usually our input is an x and our output is a y. So what that means is if you had some sort of an equation, if you put an x value in, that you would always get the same y value back. Now, there's different ways to think of it, and we'll get kind of progressively harder. Got several examples. I just did some screenshots out of the practice here. So most of these problems we're saying determine the domain and range for the relation. So we're not even talking about the function yet. We're just talking about the domain and the range. The domain is always going to be the possible inputs or the possible x values. So I'm looking for all of the different x's that were used, and the range is all the y's that we got back on that. So your domain, it does want us to put these always in interval notation if we can. Now this particular one, like I said, we're going to get harder ones. This is ultimately just a list of ordered pairs. So your domain, and on your homework, it kind of opens it up and gives you this little brace. You don't even hardly see it, it's so tiny, and you're just supposed to list out all of the x's. So you can either look at the ordered pairs that are given, that's probably easiest, and list out all of the x's. You can also look at the graph of it and just notice what's that x value, what's that, what's that, what's that. Okay, so if I look at my x values, I have a -1, a -3, a -2, and a -1. Now, I already said -1, so there's no reason to write that twice. Typically, we like to put the domain in increasing order. So the smallest x value I said there was a -3, then there was a -2, and then there was a -1. All right, so there's your domain. You turn around and you do the same thing with your range, but the range are all the y values. So you go look at your ordered pairs and say, okay, there's a -3, there's a +4, there's a -5, and a -1. Or you could look at the y values on the ordered pairs. So I think of it as the lowest because it's the y value. The smallest y value I had was a -5. That was the lowest point. And then I had a -3, I had a -1, and I had a +4. And that's my range. All right, so the second step, then they wanted you to look at this relation and decide if it would be a function or not. So remember what I said, that for it to be a function, every x value has to lead to the same, let me say that better, each individual x value should always lead to exactly one y value. And what I have here is I have an issue with this -1 x value that I had here and I also had here. When I plugged in -1, in this version, I got a -3, but in this version, I got a -1. All right, that is a prime example of what's not a function. So I would say, no, this is not a function because you have that -1 that is leading to two different y values. Now, it was nice because the ordered pairs were just sitting there. If you were looking at a graph, you're looking for anything that would have the same two x values. So if you're looking at this graph, it would be this ordered pair and this ordered pair are both left 1. So their -1 is their x value. Notice that they're lined up vertically. When we're looking at a graph, we sometimes use what we call a vertical line test, and we're looking to see if a vertical line, as it passes through the graph, ever hits more than one point at the same time. And right there it does. It hits both of those points. And then that's my clue that nope, it doesn't pass a vertical line test, meaning it did hit 2 points. And so it would not work. I'll use that vertical line test on other types of graphs, probably more so than here because I had the points to look at. All right, the other part of this, it says if you say no, you have to prove it by telling me what points are creating the problem. And they're those same 2 points we just talked about. So then you would just write the ordered pair -1, -1, and the other ordered pair was -1, -3. Those are the problematic ones. All right, so a lot of instruction on that. Now let's kind of just jump in and just do some different examples. I'm just going to give us some different graphs. The questions are the same. Find the domain and range, and then decide if you think it's a function or not. So looking at this one on the left, and these are more than ordered pairs now. So the domain on this is going to be the list of all possible x values. Now that's a little bit different because there's a lot of x values because there's a lot of points. Now I can pick out nice, pretty ordered pairs, but the reality is every point that I would draw on here would be a point I could list out. So I don't want to do that. It's what we would consider continuous. It just flows completely from left and right with no breaks. So instead, what I'm going to do is I'm going to look at what is the farthest left this graph ever gets. And looking at it, I'm the farthest left, and actually maybe what I'll do is I'll go grab my vertical line again. Let's see if I can get this. Yeah, that's kind of a fat vertical line there, but that's all right. It will work for what we're doing. Okay, so I'm going to grab that line, and I'm looking at what's the farthest left. So I kind of dragging it along, and the first thing I hit is right here. The farthest left that is landing me at -6. So that is the farthest left. So what we're doing is writing the domain and range, but they'll always want this in interval notation. So you write, maybe I should write this up here. Your domain, you're going to put it with the lower bound, the farthest, the smallest value. The lower bound is the first number, and the upper bound is the second number. So the lowest or the smallest it gets, and then the highest it gets. Now, we sometimes will use parentheses, sometimes we'll use brackets on this. And so the parentheses might be parenthesis, parenthesis, might be bracket, bracket, might be one of each. But the difference is that when you have a parenthesis, you're indicating that it doesn't quite hit that value. It comes close, but it doesn't really hit it. A bracket means it does actually hit that value. So again, you might do bracket, bracket, or parenthesis, parenthesis, or one of each. So in this case, my figure does actually hit at -6. So I'm going to do a bracket at negative, and then write -6. And then the upper bound is the farthest, the biggest it gets. And so the biggest, I keep dragging this line over here, the biggest it gets is right here. That's the biggest x value. And that's at 4. And it does actually hit at 4. So I'd say that the upper bound is 4, and I would do a bracket because it actually hit it. Okay, now we're going to do the range. The range, let me get this out of the way. I need another line here. I'm going to put in a horizontal line. So we take this, and we're looking at what the smallest, the y value is. So that's going to be the lowest my graph ever gets. The lowest it gets hits right there at 3. And it actually hits it, so that would be a bracket. And then the highest it ever gets lands right here at 8. And it does actually touch at the 8. So then I'm going to do a bracket. The lowest it is 3. The highest it is 8, with brackets on that. Okay, the second part is to determine if it's a function. I take my vertical line and I'm running it through here to see, does it ever hit this vertical line more than once? Does it ever hit more than once? Do I ever end up with the same x value going to 2 different y values? And the answer is it doesn't hit more than once. That's a good thing. That means it is a function. So I would write, yes, it's a function, and then I don't have to worry about identifying the 2 ordered pairs. All right, let's go a little faster. Here we go. Next one, the domain. The domain is the possible x values. So you're looking at what's the farthest left this graph goes, what's the farthest right it goes, because I'm looking at x values. So right here, the farthest left, well, heck, this little arrow is indicating that this is going to continue getting wider and wider, keep going up and get wider and wider. So there is no left bound or lower bound. It's going farther and farther and farther, and it actually goes to negative infinity. But negative infinity is not really a number, so you always use a parenthesis because it will never hit infinity. And so the farthest it goes to the left is negative infinity, and then it's going to do the same thing on the right. On the right, it's getting wider and going higher and higher and higher, but there's no limit to it, nothing stopping it, so it's going to go to positive infinity towards the right. Again, doesn't actually hit it, so we do a parenthesis. The range, you're looking at your y's. To do my y's, I'm going to grab my horizontal line and look at what's the lowest it ever gets. And so the lowest it is right there at -1. And it does touch at -1. So I would do a bracket on the -1. And then you're looking at what's your upper bound. What's the highest y value I ever get? Well, that's going on to infinity again because of the arrows. So I'm just going to say that it goes to infinity, and you do a parenthesis. Now, let me talk a little bit about the software on this. The infinity symbol you will get in the keypad that's on the right side of your screen. And so you use that to type in the little infinity symbol. Now, you can use just the parentheses on your keyboard. If you put an open parenthesis, it automatically puts in a closed parenthesis for you, and you would go to your keypad to put in these infinities. You can also do a bracket on your keyboard and it'll put a right bracket with it. But when you want to do something like this, when you want to have one of each, that you're going to have to find in the keypad. So you kind of have to know what you want to write and then go look in the keypad for the one that goes bracket, parenthesis, and then you can type in your info inside of it. It also has the other version where it's parenthesis bracket. All right, I got one more of these. A lot of different types of graphs. All right, I got a couple more graphs here that we're going to try. Each one has kind of its own thing. That's why I'm trying to do one of each type here. So this first example has a vertical line is your graph. All right, so the first thing they want us to do is determine the domain and the range. So the domain is your possible x values. Well, if you look at this graph, every single spot on this vertical line has the same x value. It's -4. It doesn't matter where I'm at, the x is -4. So when I say what's the lowest it can be, -4. What's the highest it can be? -4. And it does actually equal -4, so we do brackets. So that's kind of the weird thing on this one. Your range, you're looking at the y values. So you're looking how far down does it go? How far up does it go? And so those y values go from -infinity to infinity. Infinity is not really a number, so you always do parentheses. Now, when you look at it, you have to decide if it is a function or not. So I have to think of my vertical line passing through there. Will it hit the graph more than once at the same time? And in fact, boom, it hits the entire line at the same time. So yes, this is definitely going to break the vertical line test, which means it's not going to be a function. I don't want it to hit that line or that graph more than once. So no, not a function, which means I have to pick out a couple points to prove that. So I'm just going to kind of make some up at -4, 1. That's this point. And then just pick another point. Let's say -4, 0. All right. Those two would be 2 points that would, like, are straight up and down from one another, have the same x value. So I don't want them. Remember, the whole thing is you don't want that same x value to lead to different y values, and it does. So that's my proof. All right, my last one here is this circle. So again, domain and range to start with. The domain is the possible x values. So I'm looking at this and trying to think. I'm going to do this without having that line that I have to do. I want you to kind of visualize the domain is your x's. So you're looking at Horizontally, what's the farthest to the left it's going? What's the smallest x value? And that would happen right here. That's the farthest left it goes. So that has an x value of 0. It does touch at 0, so I do a bracket. The farthest to the right this graph ever gets is right here. And so what's that x value? Well, that's a 6. So there's your domain. When you're doing your range, you're looking at what's the lowest it gets, what's the highest it gets. So the smallest y value would happen right there at 1. The highest y value would happen right here at 7. Brackets on both. Now, what do you think? Is this a function? Here's my vertical line test. Does the vertical line hit it more than once at the same time? Sure does, all over the place. So that's not going to work for a function. I'm going to have to say no, not a function. And I have to prove it with a couple ordered pairs. I'm probably just going to use those 2 ordered pairs there that I was indicating earlier with, because they line up vertically. So that's what my problem is. I'm going to go with a 3, 1 and a 3, 7. There's my 2 points proving. Okay, let's move on to something different. And we're doing a lot with this domain, but after a while, we sort of want to just assume that the domain is cool. And we just, whatever we're going to plug in for X is going to work. And so we have something that we call the implied domain. So when we're working with equations and we're putting numbers in for X, we'd like to think that what we choose will work in the problem, and many, many times it does. Here's an example of a function where I can plug whatever I want in for X. There's not going to be any issues. I can plug in 2, I could plug in -2, I could plug in 22. Doesn't matter. It's just going to plug in. I'm going to get some numbers. That's the best case scenario there. If that's the case, then what we would say is our implied domain is that X can be anything, and anything to us means negative infinity to positive infinity. Sometimes you'll even get the option on your homework to just click the button that says all real numbers. That means the same thing. But there are some scenarios where you can't just plug in anything and the domain is not negative infinity to infinity. As in all those previous examples, that was not always the domain. So here are some examples of what that looks like as an equation. Here's one scenario. We have a square root. Now, you'll recall that in a square root, we do not want to accidentally end up with a negative number underneath this radical. This has to stay positive. If you try to take the square root of a negative, it's going to give you an error in your calculator. It is considered undefined. But our goal here then is to figure out what can X equal that will work, because that's what your domain is, what will work. So I've got to make sure that X minus 3 stays positive or 0. It's okay to take the square root of a 0. So what I do is I think, all right, so X minus 3 has to be greater than or maybe equal to 0. So what I want to do is I want to figure out what X needs to be. So X needs to be greater than or equal to 3. To write that, greater than or equal to 3 means 3 is going to be that lower bound, and it can be anything bigger than that. Now, if 3 is going to be okay, because it's an or equal to, then I do a bracket. Infinity is going to be parentheses. All right, we have one last scenario here that your implied domain has to be considered. You have to consider what the implied domain is, and that's on a fraction. So we know radicals, we want to keep those positive, but the thing with a fraction is we do not want the denominator to ever equal 0. You can't divide by 0, it's undefined. So I have to look at this and say, all right, well, let's restrict this a little bit so that the denominator does not equal 0. They're not being too fancy here on your homework. It's pretty straightforward. You can look at it and just kind of tell, okay, well, if X was 10, that'd be a problem, because then I'd have 10 minus 10 and I'd have a 0. So ultimately, I don't want X to be 10. But when you list your domain in interval notation, you have to tell me what it can be. So let's talk about, how do you write X can't be 10? Well, to write it, then you have to say that it can be anything less than 10. So I'm going to go negative infinity, and I go all the way up to 10. Don't stop at 9, because 9.5 would work. 9.9 would work. I go all the way up to a 10, and then I do a parenthesis to indicate it can't really equal 10, though. Now, that's only half of the answers, though, that x can be. That's kind of everything that makes it negative and makes it smaller. I also have all the values that are bigger than 10 that would work. And so we write that with this symbol in union with, and that's a symbol in your keypad. It's just this U-shaped thing. It's not the U on your keyboard. You have to go to the keypad in union with, and then you're going to do the upper part of this, which means that 10 can be anything, or x can be anything bigger than 10. But it still can't be 10. So I just pick it right back up with 10 with that parenthesis and say it can be anything bigger than that. And that's how you write x cannot equal 10. Seems a little bit lengthy. I wish we could just do x can equal 10, but that's not interval notation. All right, let's take a moment here and talk a little bit about function notation. Function notation is this g of x, or this one's g of x also. It could be an f of x. Sometimes we do h of x. And as you get in more advanced math, it doesn't really matter at all what you use. But f of x tends to be pretty common that we come across. And all that is saying that you are looking at a function with respect to x, meaning x is the variable that's involved over here in the relationship. So this is kind of like our y, in all honesty, and we'll come across that here in the next few slides. But ultimately, they're just saying, hey, this is a function, and we're using x as the variable. Now, what we're going to do here is we're going to change it up. And this is saying, okay, g is the function. And what I'd like you to do is, instead of doing g of x, instead of x being over here, we're going to do g of x squared. So what we want to do is we want to replace that x that we have with an x squared. And so then we're going to go over, and every place we see an x, we're going to replace it with an x squared. So this becomes -6, and instead of x, we write x squared minus 2. We will get to the point where we actually want to even put a number in there. We'll do that here in a little bit. Right now, we're just putting in expressions. All right, I have a few examples of this. Next one is going to be a g function again. Remember, I'm just doing screenshots, so this is a different g function. This was on a different example problem. So, but this time, what they want us to do is find g of x minus 1. So it's currently written as g of x. I'm going to replace that with a g of x minus 1, which means every place I see an x, I'm going to replace it with an x minus 1. Now, this I have to be a little bit careful of, because the x is being multiplied by 5. So that means my x minus 1 needs multiplied by 5. I need to kind of incorporate parentheses there, and then I'll do the plus 1. Because now I'm going to clean it up. I'm actually going to distribute there. And so then I have 5x minus 5 plus 1. And then last step is go ahead and simplify by combining your like terms. All right, last one. Thought I came across one that had a radical. I thought, oh, that's probably going to freak you out a little bit. So let's try it. It's again, we're just doing f of x minus 1. So it's the f function. I'm going to replace the x with an x minus 1. So big square root here. And instead of an x, I'm going to write an x minus 1 minus 4. And then that plus 6 out to the side. And then you just clean it up. X minus 1 minus 4 is really just an x minus 5. And then your plus 6 is still out to the side, and we've got it. That's it. All right, one last thing. There are some problems that are not really written in function notation, but they would like us to write them in that type of notation. So they're going to give you an equation of some sort. And it says there's 3 parts to these problems. And it says rewrite the relation as a function of x. So they want us to rewrite it so that the variable on the right side is the x, which ultimately is going to mean that we want to put everything over on the right side except for the y. And so we're going to get basically just isolate that y doing our algebra. So to isolate the y, I'm going to start undoing all the stuff that's going on. The first thing I would do on this one is, I don't like the fraction. Let's make our life easier and let's get rid of the fraction. Since we're dividing by 3, we take both sides and we multiply by 3. That's going to make that cancel out. The divide by 3, the times 3, they cancel. Then I have negative 4x minus 5y. I multiplied by negative 3 on the other side to keep it balanced, equals negative 18. All right, again, trying to isolate the y. So the next thing I want to get rid of is this 4x. So since it's negative, I'm going to add it to this side. I tend to like to write the 4x in the front. So I'd put the 4x first and then minus 18. And then your last step is to divide to get rid of the negative 5. And you have to divide everything by negative 5. Oh, I did not pick a very pretty one. All right, that's probably good. All right, so y equals negative 4/5 x. And then negative divided by a negative is going to end up a positive 18/5. So this is the function written in terms of x, because the x and all the computation stuff is on the right side. All right, so now it wants us to evaluate the function at x equals 2. So it's almost like this y is like an f of x. It's almost like they're doing that. They're replacing that. And then what they're asking us to do is to find, I'm going to write it over here, they want us to find f of 2. They want the x to equal 2. So all I'm going to do then is put in a 2 every place that the x is. So that means I got to take the negative 4/5 times 2. Well, I would like to write that as a 2 over 1, just because it's getting multiplied by a fraction. And then I still have my plus 18/5. So now we're just plugging in a number instead of an expression. And you multiply fractions straight across. So that's negative 8/5 plus 18/5. And that ends up equaling, actually very nicely, 10/5, which is really just 2. So we've got our answer there. All right, so then the last thing is says determine the implied domain. So that's from our previous slide here, found in the first step. So we're looking back up here. Once we put this into function notation right here, this was our answer to part 1. They want us to tell it what the implied domain would be. Well, this is, I know there's fractions involved here, but the x itself is not a fraction. It's not in your denominator. It's just getting multiplied by a fraction. So x can be anything I want. The implied domain would be negative infinity to infinity. All right, so that's the first one. I wanted to do one harder one. This one had a radical in it, so I thought we could practice one of those. Looking at this, I'm trying to isolate. I want to rewrite the relation as a function of x. That means put x on the right side with all the computation. The y is going to get isolated on the left. Now this is actually easier than our last one because you have just this radical here that's being added to the y. So I'm going to take this radical and I'm just going to subtract it and move it to the other side. And I'm going to be done. Y equals 4 minus the square root of 1 minus x. Now you could put the minus square root of 1 minus x in the front. It doesn't really matter. I kind of just like to leave the minus in the middle if I can. All right, so the second part of this is evaluating the function at a particular point. And so I quick edited this because the actual problem that this one had, they had x equal to 0 instead of x equals 2. So evaluate the function found in the previous step. So I'm going to look at my function that I found right here at x equals 0. So that means then I want to put 0 in where the x is. So then I'm going to have a 1 minus 0 in the radical. So now just to evaluate this, 1 minus 0 is really just 1, and the square root of 1 is just 1. So I really end up with just 4 minus 1, which is just a 3. So that's what we would get on that one. All right, so the last thing is to determine the implied domain of the function. So looking back at our function that we wrote here, remember that in a radical, you want to make sure that this always stays positive. And so I'm going to set up a scenario that says 1 minus x needs to be greater than or equal to 0, making sure. Now you might be able to do this in your head again. This one's a little bit weird because it's a 1 minus x instead of an x minus 1. A couple ways that you could do this. You could add the x to the other side, and that would be fine. You could subtract the 1, and then you'd have a negative x is greater than or equal to negative 1, but you'd have to divide by a negative 1. If you'll recall, when you divide by a negative, you have to switch the direction of your inequality. So whichever way you did this, you end up with an x has to be less than or equal to a positive 1. All right, so you want x to be smaller than 1. If x is going to be smaller than 1, you want really little numbers. So I'm going to want all the stuff that's down by negative infinity all the way up until I get to 1. It's an or equal to, so I'd put the bracket on there. All right, well, that's all I have. So hopefully you found this helpful. Good luck.